In this lecture, we would like to expand our discussion of the indefinite integral. So, as we have already seen, the definite integral of a function, of a continuous function, let's say, is defined as pretty much the set of all antiderivatives of that function. Now, to have this statement be as precise as possible, we should limit ourselves to an interval, because it's true that any two antiderivatives over an interval differ by a constant. If we have a union of intervals, then that statement is not correct anymore. But since the integration is always taking place over an interval, in the case of the definite integral, then this statement is quite meaningful. And we have seen that we can find easily a list of indefinite integrals right away. So the indefinite integral of cosine will be sine. The indefinite integral of sine, now this might require a moment of thought. What is the function that we need to differentiate in order to get sine? We know that if we differentiate cosine, then we get negative sine. And we have already mentioned the general principle that if you find a function that has derivative what you want times a constant, then you should divide that function by that constant, and that will give you the antiderivative. So here it's quite straightforward, and I'm not sure we should even use this more general principle that the antiderivative for sine x will be given by cosine x, negative cosine x plus c. Then we have the power rule that holds pretty much for all exponents with the exception of -1. So this should be a is different from -1. How about -1? Since we mentioned -1, that means what is the antiderivative of 1 over x? The antiderivative of 1 over x is ln of x, but if we just write it this way, there is a problem. Look at the two sides. The function 1 over x is defined for x different from 0. The function ln of x is defined for just x greater than 0. So it's as if we're missing a big piece of the domain of definition. It is as if we don't know, or as if this formula doesn't give the antiderivative for intervals of negative numbers. And of course, one might want to compute the integral over negative numbers. So there's this little trick that if x is less than 0, then negative x is positive, and ln of negative x makes perfect sense, right? And if we take the derivative of ln of negative x, then what we find by the chain rule is 1 over negative x times -1, which is 1 over x. So what does this mean? This means that when x is greater than 0, ln of x is an antiderivative for 1 over x. When x is less than 0, then ln of negative x is an antiderivative. Now, do we have any good way of saying x if x is positive and negative x if x is negative? And the answer is yes, we have the absolute value. So believe it or not, here we can use the absolute value, and now both sides are defined for x different from 0. And so there is a balance between the two sides. Then we have the antiderivative for e to the x is going to be e to the x plus c. And how about if we have a to the x? If we have a to the x, then we're making pretty much the same kind of remark. So if we take the derivative of a to the x, we find almost what we want times an unwanted ln of a, which is a constant. So what do? You have to divide by that constant in advance so as to ensure that what you have doesn't have the constant, because you will get a to the x ln a times 1 over ln a. And of course, these two things cancel each other. So the antiderivative here is 1 over ln a times a to the x plus c. So maybe we should have actually worked out the power rule with more examples. So for example, what is an antiderivative for square root of x? To find the antiderivative for square root of x by using the formula that we just gave, we need to think of this as x to the 1/2 dx. So with a equals to 1/2, this will be x to the 1/2 plus 1, which is 3/2 over 3/2 plus c. So this is 2/3 x to the 3/2 plus c. So that's how we can apply the power rule for derivatives. And from other antiderivatives that we could look at, let's see a few more applications of this simple principle that we gave. So imagine that somebody is asking for the antiderivative, meaning the indefinite integral of cosine of 3x plus 2. Later, we will see how to formalize this argument, but for the moment being, you can always, since you know that the derivative of sine is cosine, you can ask what happens if you take the derivative of sine of 3x plus 2. And of course, if you take the derivative of sine of 3x plus 2, this will give you cosine of 3x plus 2 times 3. So you get exactly what you want times a constant, and you just have to anticipate that constant, so you can just divide what your guess was by 3. So this will be 1/3 sine of 3x plus 2 plus c. And then another one of the same type, if we have something like x to the 5th e to the x to the 6th dx, again here, we can try to take a guess by taking the derivative of this. The chain rule will imply that the derivative of this is e to the x to the 6th times 6 x to the 5th. And you see what we get is what we want with this extra constant 6. So what is the antiderivative? The antiderivative is our initial guess. Our initial guess was this, divided by 6, meaning 1/6 times e x to the 6 plus c. And that's pretty much it. I will do one more example. Let's ask ourselves what the derivative of the third root of x plus 1 is. Now, this is kind of interesting, because if you actually find the derivative, the antiderivative for, I'm sorry, I meant the antiderivative. If you find the antiderivative for the third root of x, which according to the formula that we gave a moment ago would be x, would be the antiderivative of x to the 1/3, which is x to the 4/3, meaning we increase the exponent by 1 and divide by 4/3, which is 3. We shouldn't forget here the plus c, so 3/4 x to the 4/3 plus c. So if we find this, then nothing changes if you have, replace x by x plus 1. That's exactly what the chain rule tells you. And this means that this will be 3/4 x plus 1 to the 4/3 plus c. Again, all of these things will be will be formalized when we talk about substitution. But it's kind of interesting to note how differentiation works and try to invert that in order to see how integration works in some more interesting cases like these cases that we just saw. And that's all that we can do without any more direct and systematic methods. And our next goal will be to exactly introduce these more systematic methods. And that's all.